So now it's time to start the SmartCtrl webinar. The topic is design the control loops for a permanent magnetic synchronous machine. So the motor control or the motor drive is a wide variety. Is used in wide variety of application, like sector like electric vehicles, industrial, aerospace, some others. In this type of controls, we have a double loop, and sometimes we have a triple loop. The inner loops control the torque or the current. The second loop controls the speed of the motors, and the third loops maybe control the position of the rotor, for example. In this webinar, we implemented just double loop. So the first step, we have to know the converter plan of the permanent magnetic synchronous machine. In that case, we start with the DQ model of the motors. Also, then we are using the SmartCtrl equation editors in SmartCtrl. First, we have to design the current plan, the current loop. After that, we have to export the parameters to the simulator. In this case, we are using PSIM, but also you can use Plex or Simba on any other simulator in order to check the transient response, for example. And the second step, we have to come back to SmartCtrl in order to design the speed loop, the other loop. So this is the control structure. As mentioned before, we have a double loop. The inner loops control the Q current in this case. Also, the other loops control the speed of the rotor. This PI imposed the reference torque. We have the torque constant, and we have indirect the Q current reference. So remember that from DQ model of the permanent magnet synchronous machine, the torques depends on the D current and Q current. So the main idea here is that if you made the D current equal to zero, you can see that the torque depends only on the Q current, as you can see, and the flux. So this term, it's called the constant torque of the machine. So in the control structure, we have the PWM. Also, we are compensating the gain of the modulator gain here, and we have the decoupling axis. So in the decoupling axis, we are using the omega, but this speed is the electrical speed, it's not the mechanical speed. The electrical speed is calculated if you multiplied the mechanical speed by the pole pairs. So in the Q-axis, we have the second loop, as I mentioned before. This is the PI that controls the speed of the machine. So this is the plant. We have the current plant, and also this is the plant for the speed. So let me start with the SmartCtrl. So in that case, if I go to the file, initial dialog, this is the window that I showed you before. And here we have to go to the equation editor options. So click on here. And in this window, we have to go to the editor. And here we have to write the transfer function in analytical way. So I have this transfer function already saved in a txt file. So I have to copy this. This is the current plan. As you can see here, is the same. This is the plan that I write in the equation editor. Click on OK. Then I have to define the switching frequency. In that case, is equal to 20 kilohertz. And click on compile. So this is the frequency response of the current plan. After that, you have to click on OK. And now it's time to define the sensor stage. So in the sensor stage, we are considering a low-pass filter here. Editor, I can paste. This is the gain and the cutoff frequency equal to 1 kilohertz, and this is the transfer function of the low-pass filter. So after that, I have to click on OK, compile, and this is the frequency response of the sensor stage. Click on OK, and now it's time to select the compensator. So as mentioned before, we have three types of compensator predefined, the type 2, type 3, and PI, and also you have the equation editor. So in that case, I select the PI compensator, and here we have to define the gain, the modulator gain. So in that case, SmartCtrl calculate the modulator gain in this way. So depends of the peak value, the valley value, and also the rise time of the carrier sign. So if we want to get a modulation gain equal to 1, we have to define a peak value equal to 1, the valley value equal to 0, and the rise time equal to the switching period. In that case, SmartCtrl consider a modulator gain as 1. So I have to put here 1, 0, and in this case, 50 microseconds. Click on OK. And now it's time to select one point of the solution maps. In the solution maps, you can move the cursor. For example, I select, in this case, a crossover frequency at 300 Hertz, and for example, 60 degrees. Click on Update, and click on OK, and finally, click on OK. So this is the body plot. The pink trace represents the open loop transfer function. As you can see, here is the crossover frequency, because it's the instant when the pink trace cross with 0 dBs. And also here we have the phase margin. So after that, I have already a PSIM simulation. In this case, we have the power stage here. We are considering a constant torque load. And also I inject some perturbation. So we start with 5 Newton meters for torques, and after some times I inject 3 more Newtons per meter torque load. Also, we have the PWM. This is the typical, the sinusoidal, the SPWM. Also, we have the part transform, and we are compensating the modulator gain. And here we have the decoupling axis. And remember that this is the electrical speed. As mentioned before, the electrical speed is calculated if you multiply the mechanical speed by the pole pairs. This is the electrical speed. And then we have to use an integrator in order to estimate the theta that we are using in the part transform. So this is the decoupling axis. We have the both PI, one for each axis, the D axis and Q axis. Here we have the Q current reference. This is the constant of the torque, and here at this point we have the reference torque, and this is the PI that control the speed of the machine. Also, as you can see here, we have some low-pass filter for the currents and the speed sensor. So in that case, we have to copy the information about SmartCtrl. It's 18.966, and the TI equal to 1.8 millis. Okay. So after that, we have to design the control loop for the speed, the outer loop. In that case, I go to File, Initial Dialog. Again, I have to select the equation editor. In that case, I have to go to Editor, and here, remember that we have to use the speed plan, but the speed plan also have to contemplate the closed loop for the inner loop in that case. So let me copy this information. Okay, as you can see here, this is the momentum, the initial momentum, the parameters of the current plan. Also, we have to put here the values of the parameter of the PI for the inner loop. So I have to copy to these values to here. This is the current plant. This is the compensator for the current. Also, we have to take into account the transfer function of the sensor for the current, and this is the closed loop. This is the closed loop for the current, the inner loop. After that, the final transfer function that we have to take into account is the multiplication by the current closed loop current loop with the speed plant in that case, as you can see here. And finally, we have the return function is the way that we can say to SmartCtrl which is the plant you have to take into account for the solution maps, etc., in order to tune the PI compensator. So after that, you have to click on OK. Also, we have to define the switching frequency, 20 kilohertz. Click on compile. This is the frequency response of the speed plan. After that, you have to click on OK. Now it's time to define the equation editor for the sensor stage. I have to copy this information. Again, we have a low pass filter with a cutoff frequency of 1 kilohertz. Click on compile. This is the frequency response of the sensor stage. And finally, we have to select one of type of compensator. Again, we select the PI compensator. We have to define the peak value equal to 1, value equal to 0, and the rest time equal to 50 micros in order to define the modulator gain equal to 1. So after that, we have to click on OK, and now it's time to select one point of the converter plan. So in that case, I select, for example, a crossover frequency for 40 hertz and 50 degree of phase margin. So click on OK, OK, and now here we have the parameter of the PI. So in that case, I have to copy this for okay. 4.748 and 5.1 miles. Okay, so after that, I run the simulation. So in the simulation, we also we start with a speed reference equal to 140 radians per second. After some time, also we increase a little bit the speed reference in order to see the transient response of the control loops. And that's for the permanent manual synchronous machine. Here you can, this is all the parameters that you can find in the datasheet of the motors. And also, as mentioned before, here we are calculating the constant torque. If you know the back EMF constant that is related with this voltage. This is in PSIM. This voltage is in peak voltage by the kilo RPM. So this is lambda is the flux of the motor, and the constant torque depends of the lambda. So maybe I can see here, this is the currents, the three-phase currents. Maybe I can show you the torque reference. This is the torque reference, and this is the torque that is estimated from the motor model. So as you can see, the torque of the motor achieve the reference, and also I can see, I want to show you the speed. I think I can stop the simulation. The phase current here. This is the three-phase current, and also maybe the speed reference and the speed of the rotors. As you can see, the rotor speed achieves the reference, as I showed you before. The torque also responds, the torque achieves the reference. And also, I want to show you for example, this is the D axis current. It's set to 0, and also the Q axis current. This is the Q axis current that achieves the reference. So that is all. If you have any question, please write on the chat, or maybe you can use the option that is the P&R question section. Thank you.